So when we have summation notation, we're summing up a bunch of numbers. So for instance, this, if we wanted to work it out, we'd plug 10 in to get our first one. So 2 times 10 plus 1 is our first term, plus that goes up by 1 every time. 2 times 11 plus 1, plus 2 times 12 plus 1, so on and so forth. And we would end with 30. So 2, it's a 12 there. We write that 12 plus 1 all the way up to 2 times 30 plus 1. But it takes a little bit of work to do all those terms. So sometimes, if we can, we'd like to apply some of our formulas. I notice that my nth term here is linear. That means it's going to be arithmetic with a common difference of 2. So that's my D. Now the reason that's important, I know that for a finite arithmetic series, the sum is n over 2 times the first term plus the last term. So I need my first term, I need my last term, and I need the number of terms. Okay, well, my first term, I'd started to do it here. It's just 21. My last term, I kind of have it set up here too. It's 61. First term comes from plugging the 10 in, last term from plugging the 30 in. Now the number of terms is where you got to be careful. You might want to say that it's 30 minus 10, so 20. But you got to be careful, because when you subtract that, you subtract out the 10th term, so you have to add it back in. So it's always top minus bottom plus 1. So there's actually 21 terms in this series. So now we can use our formula to figure this out really quick without having to do out all the terms. And we get a total of 861. So if you get a summation notation and it's linear, remember that if it's linear, it's arithmetic, and you can use our formula for arithmetic. If it were exponential, it'd be geometric, and you could use our formula for a summation of a finite geometric.